Hey, I want to continue our investigation of power series, and in particular, come up with a theorem that describes where they could possibly converge. And we'll start by taking a look at an example, the sum n equals 0 to infinity of x to the n over n factorial. And if you recall that 0 factorial is 1, this is the series 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and on like that forever. As usual with power series, we use the ratio test to determine where they converge. This is the limit as n goes to infinity of the absolute value of the n plus 1th term divided by the nth term. There's lots of simplifying that happens right away. In particular, n plus 1 factorial is n plus 1 times n factorial, so the n factorials cancel. And x to the n plus 1 is x to the n times x, and so the x to the n's cancel, and you're left with this expression here. As n goes to infinity, x stays the same, so it's just a constant. We can pull the absolute value of x outside of the limit, and we're left with the absolute value of x times the limit as n goes to infinity of 1 over n plus 1. And that limit is equal to 0, so we have the absolute value of x times 0, which is 0 for any real number x. And since 0 is less than 1, the ratio test tells us that this series converges for all real numbers. Let's move on to a second example, the sum n equals 1 to infinity of n factorial times x to the n. And we'll once again apply the ratio test to determine where this series converges. It's the limit as n goes to infinity of the absolute value of the n plus 1th term divided by the nth term. And we get the same simplifications that we did in the previous problem. N plus 1 factorial is n plus 1 times n factorial, and so the n factorials cancel. And x to the n plus 1 is x to the n times x, so the x to the n's cancel, leaving us with this limit here. As before, x is a constant as far as the limit as n goes to infinity is concerned, and so we can pull the absolute value of x outside of the limit. And the limit as n goes to infinity of n plus 1 is infinity. And so for any real number x, x times infinity, or the absolute value of x times infinity, is clearly infinity, except the single possibility of maybe when x is equal to 0. 0 times infinity is an indeterminate form. And so we have to consider that case separately. When x equals 0, this series simply becomes, well, the sum of n factorial times 0 to the n. But 0 to the n is always 0, and so this series is 0 plus 0 plus 0 plus 0 forever, which is equal to 0, and so in fact does converge at x equals 0. And of course diverges for all other values of x. And so we've seen three different kinds of things happen. This example, where a series converges at exactly one point, the example before it, where the series converges for all real numbers, and in the previous video, we saw the possibility that the series might converge over some interval. Turns out those are the only possibilities. Let's look at this next theorem. And the theorem says, take any power series centered at some point A. Only one of three things can possibly happen. The series might converge only at the value x equals a. It might converge for all real numbers, or else there's some interval over which the series converges. And the interval is very specific. It's always within some fixed radius r, the radius of convergence of the center of the power series. So if it converges at a, then it converges from a minus r to a plus r, and that's the same thing as saying absolute value of x minus a less than r. Diverges otherwise, and who knows what happens at precisely the endpoints where absolute value of x minus a is equal to r. And in the first case where it only converges at one particular number, we can say the radius of convergence is 0. And in the second case where it converges for all real numbers, we can say the radius of convergence is infinite. Otherwise, this third case, there is some finite radius of convergence, r. In addition to the concept of the radius of convergence, we can also talk about something called the interval of convergence. That's the interval over which the power series converges. And in that first case where it's just at a single number, then it's the interval from a to a, so it contains only that number a. In the second case, where it converges for all real numbers, the interval is negative infinity to infinity. And in the third case, well, there's a bunch of possibilities. It's from a minus r to a plus r, and then 4 different choices depending on whether or not each of the 2 endpoints is included in the interval. Let's look at an example. The sum n equals 1 to infinity of 2 to the n times x minus 4 to the n all over n. Here we're starting with n equals 1 because we don't want to be dividing by 0 in the case where n is equal to 0. Just to make it clear, this is a power series centered at 4. The coefficients are 2 to the n over n, so those are just numbers that change as n changes, but a power series centered at 4. The coefficients times x minus 4 to the n. As usual, we apply the ratio test. And after the usual simplifications, we get this limit here. 2 and x minus 4 are both constants as far as n is concerned. And so we can pull the absolute value of 2 times x minus 4 outside of the limit. And since the limit is clearly 1, we get the absolute value of 2 times the quantity x minus 4. By the ratio test, this series converges when absolute value of 2 times x minus 4 is less than 1. And that happens when negative 1 is less than 2 times x minus 4 is less than 1. Dividing everything by 2, we get negative 1/2 less than x minus 4 less than 1/2. And then adding 4 to everything, we get 7/2 less than x less than 9/2. So this series converges whenever x is between 7/2 and 9/2. At x equals 7/2, we get the series sum n equals 1 to infinity of 2 to the n times negative 1/2 to the n over n. And 2 to the n times negative 1/2 to the n is 2 times negative 1/2 all to the n, which is just negative 1 to the n. And so this is the alternating harmonic series, which we know converges. And similarly, when x is equal to 9/2, we get the sum n equals 1 to infinity of 2 to the n times 1/2 to the n all over n. And 2 to the n times 1/2 to the n is 2 times 1/2 all to the n, and 2 times 1/2 is 1, and 1 to the n is 1. And so this is the harmonic series, which we know diverges. And that gives us our interval of convergence. It's from 7/2 to 9/2, including the 7/2, but not including the 9/2. And the radius of convergence is 1/2. This is a series centered at 4. 7/2 is 3.5. 9/2 is 4.5. Those numbers are each 1/2 away from 4. You can also see that from this line over here, because saying that negative 1/2 is less than x minus 4 is less than 1/2 is the same thing as saying that the absolute value of x minus 4 is less than 1/2. And if you recall, the theorem that we have in the third case said that there's some number r called the radius of convergence such that the absolute value of x minus a is less than r. And so r is 1/2, the radius of convergence 1/2 in this case. Okay, you try this one. Find the interval of convergence and the radius of convergence for the power series sum n equals 0 to infinity of x minus 2 to the n all over n squared plus 1. Pause the video, take a few minutes. When you're ready, start it back up. All right, we use the ratio test to determine where this converges. It's the limit as n goes to infinity of the absolute value of the n plus 1th term divided by the nth term. We can do a little bit of simplifying. X minus 2 to the n plus 1 is x minus 2 to the n times x minus 2, so the x minus 2 to the n's cancel. And then in the denominator, all I've done was expand n plus 1 squared. That's n squared plus 2n plus 1. And when you add 1 to that, you get n squared plus 2n plus 2. We can consider x minus 2 as a constant as far as the limit as n goes to infinity is concerned. And so absolute value of x minus 2 can be pulled outside of the limit. And however you compute that limit, either with L'Hopital's rule or using algebra and the limit laws, you find that that limit is equal to 1, and so this evaluates to absolute value of x minus 2. The ratio test tells us that this series converges when the absolute value of x minus 2 is less than 1. And that expression tells us right away that the radius of convergence is equal to 1. Doing the usual computation with absolute value of x minus 2 less than 1, we find that that happens when 1 is less than x is less than 3. And so we're very close to knowing the interval of convergence. We just have to figure out what happens at 1 and what happens at 3. And it's not hard to see when you plug x equals 1 and x equals 3 into this series, you get convergent series in both cases. The sum n equals 0 to infinity of 1 over n squared plus 1 converges by the comparison test when you compare it to the sum 1 over n squared. And that's enough to tell you that the previous series, the sum n equals 0 to infinity of negative 1 to the n over n squared plus 1 is absolutely convergent, so converges as well. And so here we get an interval of convergence of the interval from 1 to 3, including the 1 and including the 3. Okay, lots more fun to have with power series. You'll get some practice on the homework, finding the intervals and radii of convergence of various power series, so have a lot of fun with that. Looking forward to seeing you in class. Bye.